welcome to online instruction of MATH555. Today we will study the series solutions of second order linear equations. First we will go over the power series as we did in Calc 2. And before we say something about power series, let's first go over what is a series. A series is written in this form: C0 plus C1 plus C2. And it could be convergent or divergent. For example, this series is certainly divergent, right? Because if you add up, you'll get infinity. And 1 minus 1 plus 1 minus 1. That series is also divergent, because although they're not going infinity, but if you add up the partial sum, you will see this is 1 then 0, then 1 then 0, so it does not converge to any particular number, so it's also called divergence. On the other hand, if you have something like this, 1 plus 1 half plus 1 fourth, etc., then you will see this is getting closer and closer to the number 2. So this is this is convergence. And when it's convergent, there's a certain limit. And the partial sum will converge to that limit. That's what we call convergence. And given a series, like a sequence of numbers, how do we know if it's convergent or divergent? Well, there are many different tests. And for our power series, the most relevant test is called the ratio test. The ratio test is based on something called a geometrical series. Geometric series, which says if you add up 1 and a q and a q square and a q cube, etc., then it will be convergent if q is between -1 and 1, and the sum is 1 over 1 minus q. And that is true only for a certain range of q. I can show you why this equals that. I can multiply q to s, then get q plus q squared and q cube, etc. from each multiplication. However, I can also match it this way, because they are the same, so I can take the difference, the top minus bottom. And then you see it's just 1, because everything else cancels. So if you factor out 1 minus q and move to the right-hand side, you will get this. However, this is true for certain condition. You can only cancel these numbers if they approach 0. If q is 1, then this is 1, 1, 1, 1. This is infinity. This is also infinity. You cannot say infinity minus infinity equals 1, right? That's not allowed. But if it's convergent, then you can do that. When is it convergent? When the term approaches 0. And that is true when q is between -1 and 1. If q is beyond this range, then it's divergent. So, geometrical series has a known summation for a certain range. Now, what is the ratio test? Ratio test says if you have a series like that, C0 plus C1 plus C2, then you can just take the ratio, Cn plus 1 over Cn. If it's a geometric series, then the ratio will be a constant called Q, right? If it's not a geometrical series, then this is not a constant. But if we say the ratio for large n is a limit that is less than 1, then we can say this limit just acts like this q, because for large n it's decreasing by this almost constant ratio, so we can say it's convergent. So we say the sum of this series, this series written in the summation form is convergent. On the other hand, if the ratio is converting to something more than 1, then it's divergent. Because it's growing up like a power series or like a geometrical series with Q more than 1, then it's divergent. And why we have the after value here? Because if the ratio is not, let's say, less than 1, but it's negative 1/2, it's also convergent. Because the Q could be between negative 1 and 1, then it does not have to be positive. So we'll put the after value here. So that's called a ratio test. If we take the ratio of the series, of the two subsequent terms in a series, and then take the after value, it's convergent to something less than 1, the series is convergent. If it's convergent to something more than 1, then it's divergent. If it equals 1, then it's unknown. If it equals 1, then it's undetermined. Undetermined. It means we need some extra test to see if it's convergent or not. Alright, let's see an example. Suppose we have a series like that, 1 plus 1/2 plus, let's say 4, this is 2, this is 8, this is 3, this is 16, this is 4. You can see how it goes, right? Because the numerator is 1, 2, 3, 4, and the denominator is 2, 4, 8, 6. So this series is not a power series, is not a geometrical series, because the ratio is not a constant. But we can say it is convergent. Why? Because we can write down what is Cn first. So what is Cn? Well, if we call this C1, then we can see the numerator is just this n, right? This is C1, this is C2, this is C3. And denominator is 2 to the nth power. So this is 2 to the first, 2 to the second, etc. So let's find out the ratio. What is the ratio? This is n plus 1 over 2 to the n plus 1. And this is n over 2 to the n. Then you need to flip this when you do the fraction division. And you can cancel this to get 2. And what's the ratio of n plus 1 over n? It's not constant, but for large n, it will converge to 1. So this will converge to 1/2 for large n. And that is certainly less than 1. So we can say for large n, the ratio of two subsequent terms is almost 1/2. So we can say it's convergent. Alright, so that's what we say about a series that is not a geometrical series. We take the ratio test and conclude if it's convergent or not. Alright, now let's move on to power series. So a power series centered at x0 is written in this form. It's a0 plus a1 x minus x0, a2 x minus x0 squared, etc. And this is regarded as a function of x. So x is the variable. You can plug in x into, and by plugging the value of x here, so you get a series of a different x, you get a different series. And this series may or may not converge. It converges for certain x, but not all x. Well, depends. For some series, it converges for all x. And there's something obvious. If x happens to be x0, then this term is 0. This is also 0. Everything is 0, then of course convergent, because there's nothing but the first term. Right? But other than that, you have an infinite series, so it may not be convergent. Alright, so let's see. How do we know if this is convergent or not? We can use the ratio test. Okay? So what is the ratio test? Let's say what is the nth term? The nth term is called Cn, and in this case it will be an times x minus x0 to the nth power. Right? So it will be a product of the quotient and the power function. And by the way, that's why it's called power series, because it contains a power function. So let's take the ratio test for that. So if you do Cn plus 1 over Cn, then you get an plus 1 x minus x naught to the n plus 1 over an x minus x naught to the power n. Then you can cancel this power to get this. And we will take the absolute value. This is our absolute value here. Okay. Then we will take the limit, right? So the limit of this will be equal to the limit of that times that number. And the good thing about this limit is when n changes, this term does not change. So it's just a constant factor. So we only need to figure out this limit. And then say we call this limit L. And if this L is less than 1, or it doesn't matter what it's L. If this limit is called L, then L times that fixed number will give us the convergence or divergence criteria. So let me write down. So if the limit of A, which is the quotient of this ratio, the ratio of the coefficients is called L. Then L times this less than 1 implies convergence. And L times that more than 1 will imply divergence. So it means this x minus x naught, when it's small, this is less than 1, it's convergent. When this is large, it's divergent. And the boundary case is equal to 1. So we can rewrite this thing here as less than 1 over L or more than 1 over L. And this number we call it R. And this R is the so-called radius convergence, because x minus x naught less than R means this is x naught, this is x naught plus R, this is x naught minus R. So in this interval, x minus x naught absolute value is less than R. And this is like a circle. This is the center, this is the radius. So this R is called a radius of convergence. And actually it's called a radius because this can be extended to complex planes. So it's like an actual circle there. But here it's an actual interval. So when x is in this interval, it's convergent. When x is outside this interval, it's divergent. So this is called the domain of convergence. Domain of convergence. Okay, this interval. And outside that is divergent. On the boundary, it's more tricky because we need to do extra work to see if it's convergent. But for most purposes, we don't really care that much about the boundary. We just say inside this interval it's convergent, outside this interval it's divergent. And how do we find out this interval? Of course, the center is given, and all we need to know is to find out the radius. And the radius is given as the reciprocal of the L, where L is the limit of the ratio of the coefficients of the power series. Okay? Now let's see an actual example. Okay, first example is summation of x to the n over n. And because n cannot be 0 in the denominator, so let's start from 1. And since the power series is x to the n, so we can say the center must be 0, right? Otherwise it will be x minus x naught. So we know the interval would be between some negative number and some positive number. All right, let's take this ratio test. So find out this L. What is L? This L is the limit of the coefficient, the ratio of the coefficient. Okay, what is, we wrote out AN down there. What is AN? AN is the coefficient of this power series, which is 1 over n. Right? It's not n, it's 1 over n. And this, you just replace n by n plus 1. You get that? Then flip them around, so you get n over n plus 1. And after value does not really matter because it's a positive number. And you can see this will be 1, right? Because, for large n, it's the ratio to 1. So what does it say? L is 1, then the reciprocal is also 1. It means the radius is 1, so the interval is between -1 and 1. That's the domain of convergence. Right? And beyond this interval is divergent. And if you read it here, then it's kind of interesting because if you want to study this boundary value, then you can see if you plug in 1 here, this is 1 over n. And we know this is divergent because it's a harmonic series, so this is exclusive because that point is divergent. But if you plug in x equals -1, it turned out to be convergent. So to be precise, this is the domain of convergence. But usually we don't worry about that. We just say the radius convergence is 1. Right? Let's see one more example. And this one, we will have a power series with a factorial in the denominator. We can start from 0 so as you regard 0 factorial as 1. So if you write out it as an explicit term, you will have the first term is 1, because when n equals 1, this is, when n equals 0, this is 1 over 1. That's also 1. And it has x over 1 plus x squared over 2 and x cubed over 6, etc. And this power series is also centered at a 0. All right, let's find out the radius convergence. So let's take the limit of the ratio of this coefficient. This coefficient will be 1 over n factorial, and on top it's n plus 1 factorial. All right, then if we do the cancellation, well, first we need to flip it, then do the cancellation. By the cancellation of factorial, you will see it's just 1 over n plus 1. And what's the limit of that? If looking at n equals infinity, you get 1 over infinity. You get 0. Okay, 0. What does that tell us? If L equals 0, then what is R? R is the radius convergence, which is the reciprocal of 0. What is the reciprocal of 0? It's infinity. Right? What does that mean? Is it good news or bad news? Well, it is good, because it means the radius infinity, it means centered at 0 equals infinity and infinity. So the domain of convergence is actually everywhere. That's the domain of convergence. And that means this power series converges for every x on the real axis. And that's really good, right? Because we want it to be convergent as much as we can. And if you remember, this is not a random function. This function is just an exponential function with e based. E is that 2.71828 number. And if you remember more, you will see this to that is the so-called Taylor series. And the Taylor series is a way to write out a given function as a power series. So far we have seen a given power series, and we try to see whether it's convergent or not, or sometimes we can see what it converges to. But if you are given a function to start with, can you write down the power series? Yes, you can. you use something called a Taylor series. And it's like this. If you know the function and you know all of the derivatives, then the Taylor series is summation, from 0 to infinity. And it will be centered at any point, so then we call it x naught. And if you remember from Calc 2, then the coefficient of this power series is a fraction. The denominator is n factorial, and the numerator is the derivative, the nth order derivative of this function, evaluated at the center. But be careful, this is a number. So that is a number, that's not a function of x. All of x appears only here. So if you still have x here, then it's not a power series anymore. It will be a generic function. So let's take a look at e to the x. And let's choose x naught to be 0. Alright, then this is the n factorial down there. And what is the numerator? The numerator would be the derivative, the nth order derivative of this function evaluated at 0. Well, you know the exponential function has derivative the same as itself. So no matter how many times derivative you take, it's still itself. Then you plug in x naught equals x equals 0, you get e to the 0, which is 1. And that's exactly what we have here. So we know this is the Taylor series. Okay. And let me see. Let me erase this. Okay. Let's see one more example. Let's see log x. Log x, on the other hand, it's a function that's not as simple as e to the x. Because expanded, its derivative will change, right? But still we can trace it. So if you expand this function at the power series, you cannot expand it around 0, because what is log 0? Well, log 0 is infinity, or negative infinity, right? So it's not going to work. We have to choose a different center. So let's choose it to be 1. Or you can choose to be anything other than 1, but other than 0, but let's choose to be 1. So let's do the summation. This is 1 now. All right, so what is this? So we need to find out all the derivatives of this function, right? So let's take it. So log x, let's take its derivative, right? So what's the derivative of that? It's 1 over x. Then its derivative will be negative 1 over x squared. Then take a derivative again. You have negative 2 over x cubed. Then negative 3 will give you negative 6 over x to the 4th. Right? Let's do one more. So this gives you negative 4. So it's 24 over x to the 5th. And you can see what's going on, right? Numerator will be an alternating number of the factorial. Okay, now, remember you have to, sorry, this is not x. This should be evaluated as 1. Okay, my mistake. So then you have to plug in 1 to the derivative. So what is log 1? It's 0. This is x equals 1. Then this is 1, this is negative 1, this is 2, this is 6, negative 6, this is 24, etc. Alright, then we can sum up and write down the power series. So log x would be, let's write down the, okay. So let's see what is this in general, okay. This is n equals 0, n equals 1, 2, 3, 4, 5, right? You know, n equals 0 means its original, 1 means first order derivative, etc. So this is n equals 5, and that's what you get. This is n equals 4, that's what you get. So from these numbers, can you write down what is f to the n evaluated 1? Well, you can see this number is just a factorial, right? But not n factorial, it's n minus 1 factorial. And you have an alternating number. So you have a negative 1 to the power. What power? When it's even number, you have negative power. Oh yeah, you have negative 1. So this is n minus 1, right? Because when it's odd number, you have negative, odd number you have, this is even, so you get positive, right? So when we have this, numerator would be negative 1 to n minus 1 over n factorial and x minus 1 to the n. Right, that's what we have. And I have to take out one term because when n equals 0, you don't have negative 1 factorial. There's no such thing. So what we really have is we need to write down what's the first term. The first term happens to be 0, so we just throw away the first term. But in general, you need to write down what's the first term. It has to be log of that center, which happens to be 0. So then we can do some cancellation. You can see this n minus 1 factorial cancel that. You have nothing but n down there. So that's what you have. Alright? And if you find it a little bit hard to understand, we can write out it more explicitly. So log x equals a sum of a lot of terms. So the first term is n equals 1. You plug in here. This is 1 over 1, which is still 1. And n equals 1 gives you that. And the next term is negative x minus 1 squared over 2 plus x plus 1, x minus 1 cubed over 3, not 3 factorial, it's n. Then x minus 1 fourth over 4. Right, this is n, that is also n. So it's alternating with the denominator just being the power. And of course, it's going on forever. So that's your logarithm function. Okay? And actually, you can see this is very similar to what we have over there. X n to the n. And this is same as that, except the center is not 1, it's 0. And also we don't have this negative, alternating negative power. But they're related. This cannot be written as a logarithm. Okay, and turn out that this is nothing but negative. This is nothing but negative log 1 minus x. Because when you expand that, this negative 1 would cancel that negative power, and this negative will give you everything back to positive. Okay? So, we have seen enough power theories. And let me see, power series. Okay, we have also seen what is the Taylor series, and we also see what is the domain of convergence and how to find it. Oh, by the way, what is the domain of convergence of this? Well, you can see, to find a domain of convergence, you need to know what is the coefficient, right? And the coefficient is this. And if you take the ratio of the coefficient, you will see it's same as that, because we will take opposite value, so this will be gone, right? So the domain of the radius convergence is just like that example, which is 1, right? You can see it's the an over n plus over an, and that value is same as 1 over n down there, 1 over n plus 1, and you flip it, it's still converted to 1. So L equals 1, and that's L, so R also equals 1. So the domain so the radius convergence is 1. But don't forget that the center is not 0 anymore. Where is the center? Center is 1. So the domain of convergence for this series of convergence equals from 0 to 2, because centered at 1, 1 minus 1, 1 plus 1. Right? And if you are curious, you can check what's going on this 2 endpoint, but if you just leave it like that, it's also fine. Okay, and that's it for today. We'll continue next time.